it's not yet clear how we go from, let me flip backwards. It's not yet clear how we go from this equation here to the effectiveness NTU relationship. So let's do that. Let's just walk through that. It'll be the same thing, right? They're equivalent. There it is. Should have just gone that way. So how do we go from that equation up there to an effectiveness NTU relationship, knowing that we have the definitions that we've given here? Well, it's just a bunch of math. Let's go through this stepwise so you can see it. So let's start by saying let's solve like this equation here in terms of temperature, and then let's substitute in our definition for effectiveness where we can. So let's rewrite this. We're just going to say TC out is equal to TC in plus Q dot. So Q dot is effectiveness times C dot min times TH in minus TC in. Then that term is divided by C dot C. TH is similar, so TH out is equal to TH in minus, just because of the flipped around there, so minus Q dot, so epsilon C dot min TH in minus TC in over C dot H. Bless you. So okay, we have that. Now let's take our TC out and our TH out and substitute it into that ln equation up there where those things appear. So you get this kind of mess, but you'll see where we go with it. So we have ln, this whole big thing here, which is TH in minus epsilon C dot min over C dot H times TH in minus TC in minus TC in. Okay, that's the numerator, what that becomes. In the denominator, we have TH in minus TC in minus epsilon C dot min over C dot C times TH in minus TC in, end of quantity equals minus UA times 1 over C dot H minus 1 over C dot C. OK, let you copy that down. So what can we do here? So we can kind of rearrange this a little bit. You have TH in here and here, TC in here and here. So we can rearrange it a little bit to simplify it. And that becomes down here, fit this in, ln of TH in minus TC in times 1 minus epsilon C dot min over C dot H divided by TH in minus TC in times 1 minus epsilon C dot min over C dot C equals minus UA 1 over C dot H minus 1 over C dot C. OK, extracted stuff out. So what does this tell me? Now I can, I guess, cancel this part out right here. That goes away. But we're kind of like, you know, if we're trying to move forward with this, we're a little bit stuck because we have C dot min appearing, we have C dot H, C dot C. You know, so you kind of need to know like which is it? Is C dot H the C dot min or is it max or what? So for our purposes, actually, at this point, we just need to make an assumption. We need to make an assumption that one or the other is bigger, and we just go with it. And then the math ends up actually working out either way. So it doesn't matter which way you go, you just have to pick something and move on. So let's make the assumption, so assume that C dot, what did I say, C dot H is equal to C dot max, and C dot C is equal to C dot min. And then substitute those in. And we end up with, wish my slides were bigger, but we have ln of 1 minus epsilon. Now this is C dot min over C dot max divided by 1 minus epsilon C dot min over C dot min, which is just 1. So like that. Well, let me do it like this. Right, like this. And then we have minus UA 1 minus C dot, what do you say, C dot max minus 1 over C dot min. Okay, so progress. Oh, and rewrite this a little. So we can bring out our C dot min. I'm going to cheat. I'm going to do this. I don't want to rewrite this again. So let's cheat. Let's divide this by C dot min. And I'm going to write this as C dot min over C dot max minus 1. OK. All this like tedious math, but we're slowly seeing where we're going. So this now, this here, C dot min over C dot max, that's my capacitance ratio. So finally, I can rewrite this. My very final simplified solution is ln 1 minus epsilon CR over 1 minus epsilon is equal to UA over C dot min. That's familiar, maybe. That's NTU minus NTU times CR minus 1. So this is the final thing here. OK, solve it for effectiveness. That becomes this equation. I won't make you solve it for effectiveness. But it's the same thing, right? So that's where it comes from. Solve this equation for NTU, and it becomes this. So if you ever find yourself in a situation where like you're taking this from a table, and then you plug it in, and then you take this from a table and plug it in, that's wrong. Don't do that. Right? You are using exactly the same equation twice. So don't do that. Just pick one of them. This gives you a relationship, and you can use it. What's it say about that? So you can get these out of ease. I'm not going to show it because I think you can do that yourself. But if you go to ease and go to the variable or the dialog, right, the one we always go to, these functions all exist. So you can toggle through. I showed it to you last time, in fact. You toggle through, and you can get the relationships for effectiveness NTU. So again, the way that you would use this is you do your energy balance on the fluid. You can use an effectiveness or NTU relationship to then compute the performance for that third equation. So what we've done in these plots are for a given configuration, you can plot the effectiveness of the heat exchanger as a function of the number of transfer units. So let's say for most heat exchangers, you're probably going to want effectivenesses that are pretty high. Because otherwise, what's the point? So you want to be transferring as much of the heat as you can. So normally you're going to be looking for something that's like, let's say 0.8 or 0.9 or something like that. As you go higher and higher in effectiveness, you need more area. You need more heat exchanger to accomplish that. And this kind of shows that relationship. So let's say I have a balanced flow where capacitance ratio is equal to 1. Both the capacitance rates are the same. In that situation, this is going to be the performance. I just look at the normalized size, number of transfer units, and I might decide that for a capacitance ratio of 1, I might want to have NTU of 4 if that's my kind of goal to get to 80%. As you start getting imbalanced, now the lower capacitance rate fluid, that's going to be limiting your heat transfer. So you essentially have, with the lower numbers of capacitance ratio, you're going to have basically too much area for the same, for the same flow on the other side. So in that case, now you start bumping up your performance or your effectiveness because that lower capacitance rate fluid is limiting the heat transfer in the system. So you get up to capacitance ratio of 1 or of 0. I'm sorry. That's a case where you basically have like one fluid that's rocketing through at infinite mass flow rate. The other one is at normal mass flow rate. Or you think of like a phase change system where the temperature is constant as a function of energy addition. That would be capacitance ratio of 0. So that is shown on the top. So everything else kind of lies in between that. So it's kind of cool to map it out. The other thing just to take away, to put this in your brain, if you're doing a counterflow heat exchanger, NTU should always be, let's say, between 1 and 6 or 7. If you compute something and you have an NTU of like 50, you are paying way too much for that heat exchanger. Right? It's not helping you, assuming it's not free. So, okay, we can do the same thing for, for parallel flow. So what stands out in parallel flow would be for a perfectly balanced heat exchanger, the best effectiveness I could ever get is 50%. Not very good. As you go to capacitance ratio of 0, you'll notice these two solutions actually converge. So parallel flow, counterflow have exactly the same solution for capacitance rate of 0, or ratio of 0. Why is that? Well, I guess because if one temperature is not changing as a function of position, which is what that implies, then it doesn't matter which way you plummet. Right? It's the same thing either way. Okay, you have this down here. This is kind of a mix of the two. But yeah, there's some interesting stuff there. Okay. Last thing here. We'll give you a few extra minutes today. So the last thing here is going to be, you can plot these things out. So let's think about the relationship between the temperature profiles in the heat exchanger and the size of the heat exchanger, the NTU of the heat exchanger. So starting with, let's say, a parallel flow. If I have let's say a finite NTU, a relatively small NTU, maybe this 1 or half or something like that, you have fluid coming in. You're not exchanging all the heat that you theoretically could. So what's going to happen? You're going to have the fluid kind of comes in and meets, or gets to this point, and then you leave the heat exchanger. As you make this heat exchanger longer and longer, let's say, you're eventually going to get to a situation where these two fluids are going to approach each other at some temperature, at some point. This is for CR of 1. If it wasn't for 1, they'd meet at sort of whatever weighted position would correspond to that. But so you eventually get to this point where you do converge, and this is why we say you're wasting heat exchanger area, because at this point on, you might as well have not paid for that part, right? You've already accomplished your goal, so you don't need any more. So that's for a parallel flow. For counterflow, you have a slightly different situation. So this is for a balanced heat exchanger again, capacitance ratio of 1. You can see that the two temperatures track each other. This is for finite NTU. Now what happens if you go to infinite NTU? You actually get the two lines will sort of collapse onto each other. So you're maintaining exactly the same temperature profile through both, but they are just differentially apart from each other.